Chapter 1, Section 1.8, Combinations of Functions, Composite Functions. Here are the section objectives. We'll start with the arithmetic combinations of functions. These four are sum, difference, product, and quotient. And you can see the definition of each. If it says f plus g of x, that means you take f of x plus g of x. I'll show you an example of that one. And all of these are very intuitive. The difference of two functions just means you subtract the functions. Product means you multiply them, and quotient means you divide them. Let's do an example of a sum of two functions. We'll first find f plus g of x. The definition is f of x plus g of x. So what you do is you take the f function, then you do a plus, then you take the g function and combine like terms. So f of x is 2x plus 1, g of x is x squared plus 2x minus 1. And when you're combining functions, you're not solving. You don't set it equal to 0 and solve. You're combining like terms. That's how you simplify, and then you're done. So we'll combine like terms. X squared plus 4x are 1, and negative 1 would cancel out, and that would be it. So adding two functions together just means you write them with a plus in the middle and combine like terms. Then evaluate when the sum is x plus 3. How you'd write that is f plus g of 3. And what you could do is you could do f of 3 plus g of 3. You know, plug in 3 in the f function for x, plug in 3 in the g function for x, or since we already did f plus g of x and simplified, I'm going to back up and I'm going to plug it into the simplified version of the sum of the two functions that I already have. So 3 squared plus 4 times 3. It'd be 9 plus 12, which is 21. Here's the typed out solution. Now a composition of function is noted with a small o. When I downloaded the PowerPoint from Cengage, it changed all the composite or the composition symbols into rectangle with X in the middle, and it should actually be F composite G of X. It should have a little O there. So I'll try to catch all of those and fix them. But what a composition means when you have a composition of two functions, it means you're going to run the X through the g function first, and then whatever your answer is there, you'll run that through the f function. The definition is noted here, and that is what you'll see me write over and over. So let's do a couple of examples. First, f composite g of x. Next, g composite f of x. And then part C is g composite f of negative 2. So let's start with part A. F composite g of x. So composition means you are going to run the x through the g function first, and then that expression through the f function. The definition is written like this, and what we do is we start on the middle, or we start on the inside with g of x. So I'm going to replace what's underlined in blue with the g of x function. So f of, what is g of x? It is 4 minus x squared. So that was me plugging in x into the g function. Now you can see what I have written is f of 4 minus x squared. So I'm going to take 4 minus x squared, and I'm going to plug that in the f function for x. So f of x is x plus 2, so it's going to be 4 minus x squared plus 2. So again, you saw me plug x into the g function, and then I had to take the whole g function and plug it in for x in the f function. Then I'll combine like terms. That would end up being 6 minus x squared, or you could write that as negative x squared plus 6, either one. Then for part B, we will flip them. Now this one is G composite F of X. Completely different problem. You cannot flip them and get the same answer, so we'll have to start over. The definition would be G of F of X. What we do then is we start with F of X. We start by plugging in X in the F function, so it's just G of whatever that is, which would be X plus 2. Then we do G of X plus 2, which means we take X plus 2 and plug it in the G function for X. So it'd be 4 minus X plus 2 squared. So see how that X plus 2 got plugged right there in for X. It's getting kind of messy. All right, so then I have to simplify. Simplify is just getting rid of the parentheses and combining like terms. So I'll have 4 minus X plus 2 squared. X plus 2 squared is X plus 2 times itself. That would require a FOIL. So 4 minus, and then I'll FOIL that. X times X is X squared. Outside and inside is 4X. And 2 times 2 would be 4. I'll distribute the minus, so I'll have 4 minus X squared minus 4X minus 4. Combine like terms, and my 4 minus 4 would cancel out, so I would just have negative X squared minus 4X as my final answer. Part C is G composite F of negative 2. Now I already did G composite F of X, so what I could do is plug negative 2 in for each X. That would be one way to do it. Now if you didn't have part B and G composite F of negative 2 was a problem all on its own, I'm going to show you what I would do then, just so you have, that tool available to you as well. So the definition of composite is G composite, or G of F of negative 2. And what you would do is start your way from the inside out. So you'd first plug negative 2 in the F function. F of negative 2 just means plug negative 2 in for X in the F function. That would be G of, and then that would be negative 2 plus 2. So that's the F function plugging in negative 2 for X. Negative 2 plus 2 is 0. So once you do that gray underlined part, the inside part, now you're left with G of 0. Well, G of 0 is just plugging 0 in the G function for X. So it'd be 4 minus 0 squared, which would be 4. So when you have a number, you first plug the number in the F function, and then you take that result and plug it into the G function. And all that work is shown here. There's A, B, C. All right, the application is about bacteria. It says the number N of bacteria in a refrigerated food is given by this. So N of T equals 20T squared minus 80T plus 500. And it says T can be as low as 2 and as high as 14. T is the temperature of the food in degrees Celsius. When the food is removed from the refrigerator, capital T function is here. T is the temperature of the food in the degrees Celsius, and how you figure out the temperature of the food is this function, and that can be between 0 and 3, where little t is time in hours. So if you work backwards, we first have this T, which is the temperature of the food. You figure out the temperature of the food by plugging in the amount of time that it's been out of the fridge. And then once you have that, you would plug that answer in for capital T to get the number of bacteria in the food. So it says find and interpret N composite capital T of little t. So we'll start with that. N composite capital T of little t. The definition would be N of T of T. The little t and big T are kind of confusing because they're the same letter, so I'll try to differentiate those. So we will start with inside the parentheses, which is the capital T function. So you plug little t in for t, and you just get that function again. So that would be n for small t plus 2. Then I have to take this function and plug it in for capital T here and here. I have to take that and plug it in for the variable of the n function. So that would look like 20 for t plus 2 squared minus 80 for t plus 2 plus 500. I'd have to simplify that. So I'm kind of running out of space here, but it would be 20, and then I'd have to do 4t plus 2 times itself. I'd have to distribute the negative 80. So that'd be minus 320t minus 160 plus 500. Then I'll FOIL that. So I'd get 20, that'd be 16t squared plus 16t plus 4, and then I'd have to distribute that 20. So that would be 320t squared plus 320t plus 80 minus 320t minus 160 plus 500. If you combine all the like terms, there's what we get. The type solution is already there for us. It's 320t squared plus 420. So that was part A. It says find and interpret, so there we found it. The interpretation would be small t is the number of hours the food is out of the fridge. So I would say this function represents the number of bacteria found in the food after a certain number of hours. So if it's out for 2 hours, you plug in a 2, you'd get the number of bacteria. If you go back up here, B was kind of hidden now. It says find the time when the bacteria count reaches 2,000. So what we'd have to do there is say, okay, well, there's our function. We set it equal to 2,000, and then we'd solve. I would subtract 420, divide by 320, and square root t squared to get my answer. Here is the solution typed out. And when you do that, you get little t is about 2.22. Now, since you square rooted it, it's positive and negative, but since little t is time, negative 2.22 would be back in time. So we're just going to take the positive 2.22 for our final answer, and we'll say small t equals about 2.22 hours, which that is how long it takes for the bacteria to reach 2,000.